The viral headline claims mushrooms eat tires, but that phrasing obscures a massive engineering breakthrough. For 150 years, recycling rubber has been physically impossible because synthetic polymers are designed to resist degradation forever. They do not rot, they simply sit there or burn into toxic fumes if you try to destroy them. Mycocycle is not composting waste in the traditional sense. It hijacks a specific biological enzyme from white rot fungi that evolved 300 million years ago, specifically to crack open lignin, and applies it directly to synthetic rubber chains. This script pivots your understanding from nature cleaning up trash to enzymatic depolymerization as a manufacturing tool, explaining how biology is solving an industrial chemistry problem that mechanical shredding cannot touch. To understand why this matters, we must look at the chemical barrier of modern infrastructure. Synthetic tires are made of vulcanized rubber, which creates a cross-linked polymer network designed for extreme durability and resistance to heat, ozone, and biological decay. This same material composition is what makes our roads so resilient but also impossible to recycle using standard methods. Traditional recycling relies on grinding or pyrolysis. Grinding turns the tire into low-grade rubber mulch that has lost its structural integrity, while thermal processing requires immense energy input just to break carbon-carbon bonds and often releases significant amounts of CO2 in the process. The fundamental issue is that our current industrial chemistry treats these materials as waste because breaking their chemical bonds is too energy-intensive or destructive to do economically at scale. The biological mechanism behind this breakthrough utilizes white rot fungi, such as Phanerochaete chrysosporium. These organisms possess unique oxidative enzymes, specifically lignin peroxidases and laccus. As noted by Department of Energy research from David Hibbett, these fungi evolved roughly 300 million years ago to break down lignin, the tough glue that holds tree cell walls together. This evolutionary development coincides with a decline in coal formation because they could digest what other organisms couldn't. The specific hack here is that lignin and synthetic rubber share aromatic ring structures. The fungal enzymes do not just eat the surface, they perform enzymatic depolymerization, cleaving complex molecular bonds to break long polymer chains into smaller oligomers without generating CO2 or toxic byproducts in significant quantities. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Scientists used carbon-113 labeled synthetic compounds to prove that fungi don't simply excrete carbon dioxide when breaking down aromatic structures. They incorporate those carbon atoms directly into their cellular biomass and the resulting chemical products. This tracking confirms that the process is a metabolic engineering feat where the fungal enzymes break down polymer chains into usable monomers, which are then harvested or utilized as raw materials, distinct from simple digestion. It transforms what was once considered inert waste into active building blocks for new infrastructure without requiring specialized sorting hardware beyond the biological reactor itself. The output of this process challenges our definition of recycling products. Unlike composting food scraps, which turns matter back to soil and carbon dioxide, Mycocycle's process converts these broken-down tire polymers and construction waste binders into a high-value adhesive material. This re-engineered binder can replace petroleum-based asphalt or concrete additives in new construction materials, creating a circular loop where the chemical structure is preserved but repurposed rather than destroyed. The engineering payoff shifts the paradigm from disposal to biological remanufacturing. It operates at ambient temperatures and pressures, avoiding the massive thermal inputs required for pyrolysis while maintaining material quality that allows the reclaimed rubber to function in high-strength applications suitable for new roads and buildings. This approach addresses a critical scalability of waste issue where construction debris and tires are often landfilled together due to mixed streams being too expensive to separate mechanically. By turning a disposal cost center into a raw material supply chain, we bypass the physics of traditional recycling. The process does not degrade the material's quality, it chemically reclaims the polymer backbone to create high-strength binders suitable for new infrastructure projects. This is a fundamental shift in how we view manufacturing inputs, where our roads and buildings rely on materials that are effectively forever waste once they leave the factory, because breaking their chemical bonds has been too energy-intensive or destructive to do economically until now. The statistics from thermochemical data available regarding organic and inorganic compounds number over 7,000, with reactions involving enthalpy and free energy of reaction exceeding 8,000 entries. Yet the application of these specific enzymes remains a rare convergence of biology and industrial chemistry. Infrared spectral data for 16,000 plus compounds helps us understand exactly how the carbon atoms move from tire to fungus to new binder, confirming that we are not just breaking things down, but reassembling them into something valuable. White rot fungi evolved specifically to crack open lignin in trees 300 million years ago, when fossil records show trees beginning to break down due to this unique capability, making it the only major organism capable of degrading such complex structures efficiently without converting everything entirely to carbon dioxide. We are moving from a model where we burn or grind waste into low-grade byproducts, which is what traditional recycling treats tires as, toward a system that uses enzymatic depolymerization to chemically re-engineer rubber polymers back into high-value construction binders. This bypasses the energy limits of thermal processing and offers a path forward for materials that have been considered impossible to recycle since their invention over a century ago. The engineering story here is not about nature cleaning up trash, but about hijacking an ancient biological tool to solve a modern industrial problem, turning the chemical resistance of synthetic rubber into its greatest asset by repurposing it rather than fighting against its durability with brute force energy inputs. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.